All right, so chapter 19 is all about how energy changes during chemical reactions. We did this earlier in the year and we talked about delta H. Delta H it represents heat changes at constant pressure, right? We can measure them or we can calculate them using Hess's law. If I lose potential energy during a chemical reaction, right, if reactants turn to products and I lose potential energy, the difference between the potential energy lost is the amount of heat energy released. And in a reaction that is going to happen, right, it usually implies that we're going to lower potential energy, right? So exothermic reactions imply that you're going to a more stable state, implies that it's going to happen. All right, if we're talking about equilibrium, that implies a spontaneous reaction. All right, along with that, we understand that certain endothermic reactions are also spontaneous, so delta H isn't the total picture. There's also entropy. Entropy is the tendency of a system to want to go towards disorder. So if I have all the molecules in one container and I have an open pathway to the other container, the most likely outcome is having them all mixed up, right? Even distribution between the two containers. So the more disordered system is the more likely system. So between these two things, heat release and becoming more disordered, this implies whether a chemical process is going to happen or not. So a way of equating change in entropy, disorder, to enthalpy, change in heat. If I multiply delta S by temperature and I subtract it from delta H, this gives me what's called Gibbs free energy. Gibbs free energy is a combination of these two things. And if I lose free energy during a process, this implies it's going to be spontaneous. So with delta G is equal to delta H minus T delta S, you're considering both components that go into whether something happens or not. And if I get a negative value for delta G, this implies spontaneous. So along with that, we can talk about free energy changes or Gibbs free energy changes at standard conditions. When I completely change, when I look at the free energy of the products and subtract it from the free energy changes of the reactants, I can look at free energy as a state function. Right? It doesn't matter how many steps are involved, it just matters what the change is. So if I get the change in free energy and I get a negative value, that's going to equate to a big equilibrium constant. So delta G naught equates to K, equilibrium constants, Kas, Kbs, Kcs, whatever. Multiply R, the gas constant in joules, by the temperature in kelvins, by the natural log of the equilibrium constant. Multiply by -1 will give me the relationship between equilibrium constant and a loss of free energy or a gain of free energy. It's standard conditions. So if delta G naught is a way we can equate free energy changes to equilibrium constant, free energy changes not at standard conditions are a way of figuring out where are we in an equilibrium. Are we at equilibrium? Are we past equilibrium? Are we before equilibrium? So there's a way of equating free energy changes at non-standard conditions to Q, right? Remember this reaction quotient. And depending on your value for delta G at non-standard conditions, we can figure out where we are in terms of going towards equilibrium. All right, so our first problem. Number 3, what are the signs on delta H and delta S for the process predicted here? Okay, so the process was solid turning into a gas. So if I put heat energy into a solid, that's an endothermic process. I spread the particles apart. Turning a solid into a gas is disordering it. All right, so we have order when we're in a solid. We have more disorder when we're in a gas. So that's an increase in disorder, increase in entropy. So the signs on delta H are positive. I had to put heat energy in. And the sign on delta S is positive. I've become more disordered. So if I plug both of these values into this equation, delta H minus T delta S, one is working towards making a delta G negative, right? That's the fact that we're becoming more disordered. So negative T times a positive value gives me a negative value for delta G. So at high temperatures, this reaction will be this process will be spontaneous. At low temperatures, it won't be. All right, so this is what we get, the relationship between change in enthalpy and change in entropy as a way of figuring out whether we're going to have a spontaneous process or not. So I answered B there, I guess. Yeah, what might the sign on delta G be? If the energy flow in and out of the system at a constant temperature during the process, what can you say about the entropy change of the surroundings as a result of this process? All right, so if heat energy is being transferred to the system, your surroundings are becoming more ordered, right? So if the surroundings is losing heat, molecules are slowing down, they're becoming more ordered, right? You're becoming more like a solid. If I'm losing heat from the system to the surroundings, well then delta S is becoming, the surroundings is becoming more disordered, right? So in an exothermic process, the delta S sign on the surroundings is positive, and for an endothermic process, the sign on delta S is negative. That'll be important later on when we talk about the second law of thermodynamics. All right, predict the sign on delta S for the accompanying reaction. Explain your choice. All right, so I have 1, 2, 3, 4, 5 molecules going in, and at the end of this, I end up with 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 10 molecules coming out the other side. So one way of looking at increasing disorder is if you produce more particles, right? Producing more particles is making things more disordered. So going from a solid to a gas, increased disorder. Making more particles, becoming more disordered. So the positive sign on delta S. Consider a reaction between molecule A and molecule B to form 2 moles of AB. Okay. Atoms of A are shown in red in the diagram. Atoms of B are shown in blue. The K value is 1. Which box represents a system at equilibrium? All right, so I guess what we're doing here is we're counting up the number of red ones, blue ones, and red blue ones to figure out where we are in terms of equilibrium. So if I plug in box 1, there's 3 blue ones, 3 red ones, and 3 red blue ones. If I plug that into the law of mass action, I get a Q value of 1. If I look at box 2 and I count them up, I've got 4 red ones, 4 blue ones, and only 1 red-blue one. If I plug that in, I get a value for Q. And do the same for 3. 7 red-blue ones, and only 1 blue one and 1 red one. So a Q value of 49. So where are we in equilibrium? And that's really what you're asking. So if we're looking at question A, box 1 represents equilibrium. All right, so at equilibrium, right, we had a K value of 1, we have a Q value of 1. So these are the equilibrium concentrations. So at this point, if you're talking about the delta G value, which is question B, you've lost as much free energy as you're going to lose at non-standard conditions. So at equilibrium, the delta G value is 0. A delta G value at non-standard conditions represents a stoppage of the forward reaction. You've stopped going forward and you're at equilibrium. Can't lose any more free energy. Okay, and then they want to know the signs on the rest of the boxes, right? So if I'm looking at box 2, I plug in, right, Q is less than K. So I'm not at equilibrium yet, right? I still have to make more of those red-blue ones in order to get to equilibrium. So at this point, you're still losing free energy. So the sign on delta G absolute is negative. If I'm looking at box 3, I've got a K value of 1. I've got a Q value of 49. I'm way past equilibrium here. All right, so I've got to slide backwards in order to go to equilibrium. In order to get past this equilibrium point, I'd have to put energy in to do that. So this represents a positive sign on delta G absolute. All right, the accompanying diagram shows how free energy, G, changes during a hypothetical reaction where A reacts with B to form C. On the left are pure reactants, each at 1 atmosphere, and on the right are pure products also 1 atmosphere? What is the significance of the minimum in the plot? And what does the quantity x on the right side of the diagram show? All right, so there's a problem later on. We get into this in more depth, but just looking at this, the blue line represents a change in free energy. So as free energy goes down, 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 and down, you're going towards products. You're going towards A and B turning into C. Eventually, we get to a point where we bottom out. We don't lose free energy anymore. At that point, the change in delta G absolute, or delta G at non-standard conditions, is 0. This means you're at equilibrium. The reaction has stopped at this point, and you've made as many products as you're going to make, lost as many reactants as you're going to lose. Now, if we pretended that we went all the way across, all the way over to the other side, we'd get the difference between where we started with the reactants and where we ended up with the products. When I take the difference between the reactants at standard conditions and the products at standard conditions, that represents the change in G naught, or G at standard conditions. Products minus reactants. So again, what I'm doing with G naught is pretending that I completely change products into reactants. And I look at the magnitude of that value. If I have a negative value, which is what I have here, I've lost free energy at the end of this. I have a spontaneous reaction. So that's how you use G naught versus G. One is looking at reaction progress. Am I at equilibrium yet? When I finally get to a delta G absolute value of 0, let me just click back. I'm at equilibrium. And if we're looking at the difference between the delta G at standard conditions for the reactants and the products, it's a way of figuring out whether this reaction is spontaneous or not. When you stop, do you have more products made than reactants formed?